In this course, we're interested in the geometry of patterns, patterns in the plane. And in this video, we're going to explore patterns which cover just a strip of the plane. Such patterns are called friezes. Although there are infinitely many frieze patterns, we'll find there are actually just a small number of distinct types, 7 in fact. And by using an algorithm based on a few simple questions, you'll be able to determine the type of any given frieze. But first, let's make sure you know just what we mean by a frieze pattern. The friezes we find in the real world always have a beginning and an end, or they're wrapped around some object, like this vase. But what we're going to deal with is a mathematical abstraction, an infinitely long frieze. If we unwrap this frieze from around the vase, then we can unroll it indefinitely far in either direction. And that demonstrates an important characteristic of a frieze. It should exhibit some sort of pattern. What pattern can you see in this frieze? This frieze pattern is repetitive. That is, it has translational symmetry. If we take a copy of the frieze and move it along, eventually it coincides exactly with the original. Clearly, there's a minimum distance through which we have to move the frieze before this happens. This gives the translation we'll call t. The same thing happens if we move twice that distance, or indeed any multiple of the distance, including negative multiples, corresponding to displacements in the opposite direction. We're not going to consider friezes like this one. No matter what distance you move it through, it will never match itself. But what about this frieze? Does it have any kind of repetitive pattern? This pattern always matches, whatever distance you move it through. There's no minimum distance of translation before the copy matches the original. We're not going to consider friezes like this either, because in effect there's no interesting repetitive pattern. So, what we refer to as frieze patterns are friezes like this one, where there is a minimum translational symmetry. We'll always draw our friezes horizontally, so the translation will be horizontal also. Well, now that we've defined exactly what a frieze pattern is, we can begin the task of classifying them. Well, actually what we're going to do is to identify all possible symmetry groups of frieze patterns. We say that two frieze patterns are of the same type if they have the same group of symmetries. Now, there's no point looking for translational symmetries. All frieze patterns are the same in that respect. Otherwise, they don't count as frieze patterns at all. So, what other symmetries can we investigate? What symmetries does this frieze have? Well, look what happens when we put a mirror across the frieze. The reflection of the pattern in the mirror is identical to the original pattern. So this frieze has a reflectional symmetry in a vertical line. We'll call it V. Now, to find more symmetries, we could try performing the reflection twice. But that simply gets us right back to where we started, because V is its own inverse. That is, V composed with itself is the identity E. But what about this frieze? It doesn't have any reflectional symmetries in vertical lines, but it does have a symmetry about this horizontal line. We'll call this the reflection H. As you'd expect, H composed with itself is again E. Now this frieze doesn't have any reflectional symmetries. But if I turn it around, like this, then you can see that there's a rotational symmetry. We'll call this the rotation R. Again, R composed with itself is E. But what about this frieze? There are no reflections and no rotations, but surely there's something more than just translational symmetry. Well, if we reflect in the horizontal midline, it doesn't quite match. But if we move it along, then it does. Since this is a little bit more complicated, we'll put a mark on the frieze to see what's going on. The symmetry we've found is a glide reflection. We'll call it G. It's a composition of a horizontal reflection followed by a translation. But notice that the glide reflection has only moved the mark through half the distance of the minimum translation T. So what happens if we compose G with itself? I'll perform it a second time. And now look at the mark. Performing G twice has given just the minimum translation T. So G composed with itself is T. Now, it's not only glide reflections which can be regarded as the composition of a translation with another symmetry. Any symmetry can be written in the standard form. That's the composition of a translation T with a particular rotation or reflection, X. We shall always try to get composites back into this standard form. For example, how can we get the composite VT back into standard form? Now we're ready to begin classifying friezes. We'll do it by looking at their symmetry groups. And as we proceed, we'll find typical elements of the groups and relations between those elements. As we've mentioned, there are only a small number of types of frieze. So let's take a variety of friezes and see how we get on. Well, first, let's see if we can distinguish these friezes by looking at vertical reflections. As you've seen, this frieze has a reflectional symmetry in a vertical line. So its symmetry group has an element V with the relation V squared equals E. What more can we say about the symmetry group? For example, how does V compose with translations? Well, the composite TV is already in standard form, so we'll just leave it like that. But what about the composite VT? What relation do we need to turn this into standard form, with T on the left? Well, somehow we have to move the translation past the reflection. And here's a trick we can use. Look in the mirror. You can see that the displacement of this translation becomes a displacement in the opposite direction when it's reflected in the mirror. So we can move the translation past the reflection by reversing its direction. That means V composed with T is the same as T inverse composed with V. Do any of the other friezes have vertical reflections as symmetries? Well, these two do. So we'll put them in the same class as the first one for the moment and examine them later. On the other hand, these four friezes don't have reflections in any vertical line. So their symmetry groups must be different. And we'll put them in another class. So we've divided all our frieze patterns into two classes. Those with vertical reflections and those without. An obvious next step is to look for horizontal reflections. Now this frieze doesn't have any vertical reflections, but it does have a reflection in its horizontal midline. So its symmetry group has an element h with the relation h squared equals e. Again, we need to consider composition in this symmetry group. In particular, we need to get the composite ht back into standard form. And to do this, we can use the trick with the mirror to help us again. This time, the reflection has no effect on the displacement. The translation is still in the same direction. So the symmetries commute. Do any of the other friezes have horizontal reflections as symmetries? Well, no. These other three friezes have no horizontal reflections, so their symmetry groups are different, and we'll put these friezes in another class. But what about the friezes in this class? They already have vertical reflections, but we can still look for horizontal reflections. Again, that splits them into two more classes. And in this case, where we have both vertical and horizontal reflections, we find an additional relation. The reflections composed in either order give a rotation through half a turn. What next? Let's look at the three friezes in this class, which have neither horizontal nor vertical reflections. Now we're going to look for glide reflections. Well, this frieze has a glide reflection as a symmetry. So its symmetry group has an element g with the relation g squared equals t. And again, we need to get the composite gt back into standard form. Actually, g has no more effect on t than h does, because the translation is also parallel to the line of reflection. So the symmetries commute. Do either of the other two friezes have glide reflections as symmetries? No, they don't. So these two friezes have symmetry groups which are different from the first frieze. So we'll put them in yet another class. And similarly, we can separate the friezes in this class into two further types. Those with glide reflections and those without. And in this case, where we have both vertical and glide reflections, how do we relate the composites VG and GV? In fact, we have this relation. But why should it hold? See if you can work that out for yourself. Let's see if we can now complete our classification of friezes. There's only one other kind of symmetry to look for: rotations. This frieze does have a rotation. Its symmetry group will have an element r with the relation r squared equals e. How do we turn the composite RT back into standard form? Well, what happens to a displacement to the right after rotation? It becomes a displacement to the left. So we have the relation RT equals T inverse R. Does the other frieze we've got left have any rotations as symmetries? It doesn't. So its symmetry group will be different. It's a different type. We've now run out of symmetries to check for. So let's review what we've done. We've identified just 7 distinct types of frieze. Also, we've developed an algorithm which enables us to determine the type of any frieze pattern by asking a few simple questions. Are there vertical reflections? Are there horizontal reflections? Are there glide reflections? Or are there rotations? We always ask these questions in the same order, but in some cases we stop asking questions sooner. Because our questions concern symmetries, what we've really done is classify friezes according to their symmetry groups. Now it's time for you to try the algorithm out for yourself. Try classifying this frieze. Here is how you should have worked it out. At the beginning of the algorithm, the first question is, does this frieze have any vertical reflections? And the answer is no. So now you know that the symmetry type of the frieze will be found somewhere down this branch of the algorithm. The next question is there a horizontal reflection? Again, the answer is no. You now go down this branch and ask, are there any glide reflections? This time, the answer is yes. For example, here's a glide reflection. And that's it. There are no more questions to ask, because you now know the type of the frieze. It has the same symmetry group as this frieze. But how do we know that the 7 types of frieze we've identified are the only possible types? Might there still not be types of frieze that we haven't thought of? Well, the answer to that question is no. And for the explanation, you'll have to refer back to the video notes.